How are you, everybody who is watching this video? I would like to take this opportunity to welcome some physical students who have joined me in this very interesting class of electronics communication laboratory. But also I would like to take this opportunity to welcome some online students who are not connected with us physically, but have been connected with us with the video and audio. If it's the first time to meet me, I'm very happy to have you. My name is Olenjolain. I am a Tanzanian, and I would like to thank God who have given me this great opportunity to share with you about what I know. One precaution that I would like to give my physical students, engineering students, and even my online students, that Olenjolain does not know everything about electronics communication laboratory. I just know small portions of it, but always I have a responsibility to teach others about what I know. So in case that you've been looking maybe just the platform where you can learn about electronics communication, or you want to learn about telecommunication engineering. So hopefully this might be a good place, because we have a number of modules that we are teaching just the graduates, and actually we are trying our level best to update our contents, and we are trying our level best to make sure that we connected the concepts in mathematics, science, and the electronics with applications of communication. So we had some other previous topics that were being covered. We had a topic of datasheet. We had a topic of general introduction of electronics communication laboratory. We had a topic of analog communication circuits, and we had a topic of measurements of analog communication circuit. So we still have two main topics. This one that called digital electronics communication circuits, and also we'll be dealing with measurements of the digital signals processed by digital electronics communication circuits. So for this workshop or for this class, you just need to have a fresh mindset, and actual that you have to remember about telecommunication science or communication science. And also you should have your exercise book, your pen, your pencil, your ruler, and a rubber, because we are going to have a number of drawings, possibly minimum is 2 figures that we are going to draw, which are actually the general block diagrams of digital system or digital communication system. So remember that digital communication systems, these are one of the applications of electronics. So it's one of the particular applications of electronics engineering on solving real life problems. So let me appreciate, because always I used to appreciate people who I met them physically and even online. How are you, students? How are you, engineering students? Eh? I just hear the voice of the gentleman. How are you, ladies, in this class? So ladies are fine, but their voice has gone to vacation. Well, so let me introduce and build a foundation to you about digital electronics communication circuits. So in this topic, we are going to discuss, I build the foundations about wireless digital electronics communication system, and even analog, wired. So let us start the business and let us understand the first phenomena which you call the digital communication system. Class A, digital communication system. So digital communication system, hopefully this is the one of the phenomena that you have heard. But what does it mean? What is digital communication system? So what the meaning of digital communication system? So he said that a digital communication system, a digital communication system, we say that, does it mean that it consists only digital electronics components? So he said that is the type of communication system, the type of communication system. So this is the type of communication system whereby the signal or information signal, please observe silence. Or students, physical students, observe silence please. Or information whereby the informations or signal or the information signal, the signal or information which is required to be communicated. Which is required to be communicated, is in digital form. That's the meaning of digital electronics communication system. Seni. So this is the type of communication system whereby the signal or the information signal which is required to be communicated between the 2 points or 3 points or 4 points or 5 points must be a digital signal. So that's all. So when you say digital communication system, it may be either pure digital communication system or it may be partial digital communication system. So it doesn't mean that it consists only digital electronics components, no, because the real world is actual analog. I think that after building these foundations, I will ask you a question. If digital systems has more advantages compared to the analog system, why do we still have analog system? Why should we not phase out the analog system and remain with digital system, which is compatible and which is actual has a lot of advantage compared to the analog? So the main part is actual the type of the signal or information signal which is required to be processed or which is required to be transmitted and which is required to be received on the other side. Are we together? Are we together? Is it clear? It's not clear. Students, I don't hear your voice. You are more than 50 students. Is it clear? So when I have a digital communication system which consists only digital electronics components, can we call it digital communication system or we can't? Okay? Pardon? You said you understood. Then I challenge what you have understood. Then you are quiet. Okay. So when you say that digital signal, when you say about digital signal, which is the one of the characteristics that has been indicated here, so you say that the nature of the signal or information, the nature of the signal or information processed or transmitted or received by digital system is or has only two states. Two states. And these two states, we know that. We name them. That digital signal might have either high state or might have that, yes, a high state, and also the second state, low state. So the digital signal so the digital signal may be presented by the binary number, which we call them binary bits. So we call them 1 and a 0. So you say the binary bits represents two levels of voltage. Present two levels of voltage. So bit number 1, it may represent 0 volt, or bit number 1 may also represent 5 volt. Bit number 0 may represent 0 volt, and bit number 0 also may represent 5 volt. So it depends to the situation, and it depends to the source, and it depends to the configurations of that source of the digital signal. So whenever we teach this concept to the students for the first time, we used to teach them that one bit or bit 1 represents 5 volt, right? And bit 0 represents 0 volt. That is the fundamental skill. But for you, nowadays, you are no longer just beginners. You are kind of intermediate engineering students. So it means that it's not the issue that you should not claim that maybe 1 just represents 5 volt. No, that's not true. 1 may represent 5 volt, 1 may represent 0 volt. It depends to the applications of that signal. Similarly, the bit 0 may represent 0 volt or may represent 5 volt. So it depends. But remember that we use them interchangeably. So for instance, if you say that bit 1 represents 0 volt, then for that case, then bit 0 should represent 5 volt. And when we say that bit 0 represents 5 volt, then bit 1 should represent 0 volt. So you have to use them. You may not say that bit 1 represents 0 volt and bit 0 represents 0 volt. That will not be a digital signal. You may not say that bit 1 represents 5 volt, bit 0 represents 5 volt. Are we together? Class, are we together? Eh? Are we together? No. What didn't you understand? I heard some no's. And I always respect no's more than yes. Because many students, they used to be liars. They say yes while they did not understand. Give them the test or the exam. Then we realize. Any question you give them, it is tough for them. Pardon? Whenever we define the bits, the binary bits, so she asks the question, how and in which conditions may you define bit 0 is equal to 0 volt? That is Pili's question. So the response is this one. Whenever we define the binary bits in terms of voltage, it depends to the source of that bit. Okay? So it's not the matter that you decide. Because remember that these binary numbers represent the voltages which have been given. And remember that the binary bits actually defines different real situations. For instance, example. We can have a digital sensor. And this digital sensor, you may just define that when the signal or when the phenomena is being detected, then that we call it binary bit number 1. When the phenomena is not detected, the real world phenomena is not detected, then you may define as 0 bit. But that digital sensor will provide the bits or the two different states or the two states of the bits by using its output pin. So some of these digital sensors, you find that when the sensor did not detect a phenomena, then you find that it provides 5 volt or 3.3 volt when there is no any physical phenomena which has been detected by the sensor. Okay? And then when it detects the physical phenomena, the state of the sensor will change. Okay? Oh, sorry. We say that number 1, when the detection has taken place. And number 0, when there is no detection. Right? Right? So if you measure the output voltage that given by the sensor in those two states, when the signal or when the real world signal is not or the real world phenomena is not detected, then you might find that the output voltage at the output pin of the sensor is 5 volt. Oh, sorry. Let me start with the one that you are familiar. These are the binary bits. Number 1 represent detections of the sensor, of the particular digital sensor. And number 0 represents that there's no detection. Right? 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 We have just the two situations. Whether the sensor detect the signal or whether the sensor not detect the signal. Okay, so for that case, we say that if the sensor does not detect any physical phenomena, its binary bits it's 0. Then we can measure the output voltage at the output pin. Then you can find that 0 volt. So it provides 0 volt when there is no any detection of the physical phenomenon. Are we together? When detecting the physical phenomena, for instance, pressure has entered that place and interrupted the sensor, then by that time, the sensor provided the output signal or the output voltage of 5 volt. 5 volt. So this is the one of the digital sensor that we have in real life. So you see that bit 1 represents detection, bit 0 represents no detection. And then when there is no detection, the output voltage at the the output voltage of the sensor is 0 volt. When there is a detection, the output voltage given by the sensor is 5 volt. But also we have some family of the sensor, number of sensors or digital sensors, where that this is digital sensor, it's abbreviations of the digital sensor. When there is no detection, so number 1, when there is no detection, or let's say that we have number 1, but we say that in number 1 we define when there is no detection. So when there is no detection of 40 of the physical phenomena, the output voltage at the output pin is 0 volt. And then when there is a detection, then we can define, when there is a detection, you can define 0. So for this case, there is a detection. The output voltage is 5 volt. So this is vice versa of what you have on this side. So it depends to the source of the digital signal. Are we together? Are we together? Okay, so when you learn about sensors, you will cover this concept and you understand what am I telling you. Because according to the manufacturers, when the sensor is being manufactured, when there is no any signal is being detected, it provides 5 volts. When there is, it provides 0 volts. So you should not claim that, this is the sensor. When you take the signal, it gives out a high output voltage. No. But then you are understanding. Types of digital electronics, types of digital electronics communication system. Types of digital electronics communication system. Class A, types of digital electronics communication system.
Types of digital electronics communication system.
Well, so he said that in electronics and the telecommunication engineering, there are 2 main types of what? Of digital communication system. The first one, we call it wired or guided digital electronics communication system. The second type is called the wireless, or we call it unguided digital electronics communication system. So we have 2 types of digital electronics communication system. The first one is called the wired or guided electronics communication system, and the second one is called the wireless or unguided digital electronics communication system. Class A, wired or guided electronics communication system.
Wired or guided electronics communication system.
And then say wireless or unguided digital electronics communication system.
Wireless or unguided digital electronics communication system.
Okay. So as we've been discussing in analog electronics communication system, we define what the meanings of wired or guided analog electronic system, and also discussing what the meanings of wireless. So you know how to define those terminologies. The only difference here is just the type of the signal which will be processed by the system. But another difference is actually the types of electronics components that may process the signal. So that's the difference between them. So let us discuss the technical information which are very important for you to understand as electronics and telecommunication engineer. So the general block diagram, of guided, general block diagrams of guided digital communication system. So now we are getting in touch into the very interesting part where that many students who are lazy don't like it. Class A, general block diagrams of guided digital communication system. A. Okay. So stop writing, stop drawing, stop murmuring. Follow along, let us grow together. It's not a new concept for you. You have learnt it in some other modules. So this is input transducer. Class A, input transducer. Then the second block is called the source encoder. Say source encoder. So once the source encoder processes the information signal or the data signal, it sends, class I say stop murmuring, it sends its output to channel encoder. Then once the channel encoder processes the information, it gives its output. This is called the digital modulator. Then once the digital modulator processes the information, it sends its signal to channel. Then this is the block where you have interference of noise. This is the block of power supply unit. So the input transducer needs power. The source encoder needs electrical power. The channel encoder needs electrical power. The digital modulator needs electrical power. Digital demodulator. Channel decoder. source decoder, So that is the general block diagrams of wired, or we call it wired or guided digital communication system. So how many blocks does it consist? How many blocks does it consist?
11.
Huh? 11 blocks. So which block are you familiar with? Input transducer. Then Dennis say he's familiar with the block of noise. Why? Because he's expert in making what? Noise. So he's very interested with the block of noise. So when, okay, I think that, stop writing or stop drawing. When you analyze these blocks, you may break down or you may break them into 3 general blocks. I said stop drawing, stop writing, stop doing whatever that you are doing, including Sonia, and Alquino is looking outside. Stop looking outside. Look on the blackboard. I forgot an arrow from the channel to the digital demodulator. So you can break down. I think you remember that when we talked about analog communication system, mainly representing analog communication system just in 3 main blocks, which is analog transmitter, medium or channel, and or just we call it medium in case of analog. So you have analog transmitter, we have the medium of communication, and also you have receiver. So similarly, in case of the digital electronics communication system, regardless of the complexity of that digital communication system, you may break down into 3 main parts, which is transmitter and what? Transmitter, medium, and the receiver. So for that case, we say that, before I explain this one, let me just explain the fundamental blocks, because maybe this might be detailed to you. General block diagram of any digital communication system. So you say that in high level, any digital electronics communication system may be represented by 3 main blocks. And these are the 3 main blocks. So 4 main blocks. 4 main blocks. So these are the blocks. I said stop drawing, stop writing. This is the first block, and then this is the second block, and then this is the third block, and then this is the fourth block. That is stop writing. That is stop writing. Power line, power supply unit. So Eliakim is making lines. Not Eliakim Matthias, but Eliakim somebody. Power says power supply unit. Then the next block is called the transmitter, but we have to specify it because the third block we'll name it according to the type of communication. So this one we call it digital transmitter. We call it a digital transmitter. It doesn't mean because it does not have analog parts. No, we call it digital transmitter because it will be transmitting information in digital format. Okay? So this is digital transmitter unit. So simply we call it TX. Say digital transmitter unit. And then this one, we don't call it medium. For digital, we call it channel. Okay? So we call it what? Channel. Not channel. We call it what? Quality channel. Then the next block is called the digital receiver unit. Say digital receiver unit. So then we say that, first of all, a digital transmitter will need power. The channel depends. If it is wired, some of the wired channels might need power. But if it is wireless, then there is no need for power. Let me repeat. In case of the channel, we have wired channel and the wired channel and the wireless channel. So if it is wired channel, some of them might need power in order to transmit the information from one point to another point. But if it is wireless, the wireless channel, because it's space, it does not need power for it to transmit the digital information. So you have to be careful. So that's why you have to be careful whenever you draw or whenever you want to power the channel. But it's in rare cases when the channel needs power. Even the wired one. It's rare cases. There are some particular applications when you find that the channel needs power in order for it to transmit information from one point to another. Latifa. So this is figure 2. The general block diagram of digital communication system. So from that fundamental, today Magen is writing, but he's drawing at the time when I'm explaining the concept. Okay, so from this fundamental block diagram, we may open each block and come up with the number of blocks. Are we together? So this is the power supply unit. You might find that transmitter and receiver might share one power supply, or a transmitter might have its own power supply units and receiver might have its own power supply unit. Okay. If we have a distant transmitter, the distance between the transmitter and receiver, then the transmitter must have its own source of power and receiver must have its own source of power. So be careful about that. Should not claim that because you use the single power supply unit to power the receiver and transmitter, and then you think that in case you have a wireless communication or you have a wired but the transmitter is distant from the receiver, then you say I will use the single power supply to power it. That is wrong. It's just like you say that you may use your mobile phone battery to power your mobile phone or your father's mobile phone in Mwanza. If that is possible, you can show us that your mobile phone's battery can power your father's mobile phones in one. Can it? Huh? So you have to be careful. So sometimes you may either isolate the power supply units for the transmitter, then you say that power supply unit, maybe transmitter power supply unit. And then you may have another one that you call the receiver power supply unit. Okay? Be careful about that, because for you, I know that most of you have been cared or you have been trained how to claim. So whenever you claim something, you become not flexible, rigid to change. Okay? Yes, because you have claimed it and then you have kept in your subconscious mind. So simply power supply units, that's what you have here. So even for this case, for this block, you may have transmitter power supply unit, you might have receiver power supply unit. So you might have either 4 blocks or you might have 5 blocks. Remember that drawings are just the block diagrams, drawing flowcharts, drawing schematic circuit diagram, and drawings maybe a PCB layout. It's just a matter of thinking. You should be logically and systematically. Because I know that, I think that since I began to teach you, I taught you more than, I think that more than 20 or 30 diagrams. Right? And then I know the questions that are going on through the serious students. Sir, what the secrets? How do you master all of these diagrams in your mind? Or how can you explain them? How do they operate? So I know that the questions that maybe some of you asking themselves. So this is the response. The response is not where I don't use to claim block diagram. Never. I just want to understand how the blocks have been arranged and how the system works systematically, and then I know that after this block performs function, it just delivers the outputs to another block. After this block performs function, it delivers. So that's what I used to keep in my mind. And I'm always flexible. Whenever I find that there are some changes and there's a particular reasons, I adapt it and then update my mind. And actually, I think that it will be very disappointing moments for myself if just I find you fail to draw diagrams while I have taught you a number of block diagrams and a number of schematic circuit diagrams. It will be a shame for you and for me. Because even if you go through the diagrams that I've taught you, then you are in a very, very, very good position. Because I told you that don't expect that all the diagrams are drawings online or drawings maybe in a particular books or drawings in the particular notes. No. Diagrams are always, or diagrams of electronics or telecommunication engineering system must be drawing in your mind. Yourself, you draw them in exercise book. You keep in your mind during the exam. Once you are done, you tell them, bye-bye. Let us meet if God wishes. So you'll never keep any of them. Okay, so when we open, so as I said here, we may have 4 blocks or 5 what? Eh? Is that clear? For that case, power supply is this the block. Then we have a digital transmitter unit. So we can open a digital transmitter unit and come up with the 4 blocks. The first one, hello. The first one is called the input transducer. Say input transducer. The second one is source encoder. Say source encoder. Say channel encoder. And then say digital modulator. Yes, so these are the 4 blocks representing what? Digital transmitter unit. Are we together? But for you, you'll be just creating after channeling code, after channeling code. Next block is what? That's your style of learning. And I'm trying my level best to use different tricks to transform you. But you say, no, you can never transform me. The style I'm using is the one helped me from nursery school to here. So, sir, be careful. You just want me to fail. Okay, and then this block represents the channel. But these are, stop writing, stop drawing. So these blocks, actually, we have opened the channel. The block of channel, then you have 2 blocks. The channel will be affected by the noise. And you know there's the internal noise and external noise, depending on what? On the source. Then we have 4 blocks. Remember that I'm teaching this concept because we are going to learn about encoder and decoder. Before I teach about encoder and decoder, I have to show you where are we going to use them. Because it's something that new in your mind. So once you say that I don't want to know encoder, okay, fine. I don't want to understand decoder, okay, fine. Because you will never change this system. Okay, then for the receiver we have how many blocks? 4. 1, 2, 3, 4. The first one is what? Digital what? The modulator, or digital what? Detector, sometimes we call it detector. And then channel, channel, so then say channel decoder. I was waking somebody who was slumbering. Say channel decoder. Say channel decoder. Very good. Say source decoder. So you are concentrating to somebody who speaks loudly rather than you yourself to speak loudly. Say source decoder. So tell your neighbor, my neighbor, when you get your first, when you get your firstborns are identical twins. One you just call encoder, the other ones you call decoder. Just kulwa and doto. So tell your neighbor, make sure that when you get just identical twins as your firstborn, don't bother about kulwa and doto. There's a number of them, including Dennis. Dennis, the way he is just like doto. And then the other ones is called the output transducer. Say output transducer. Say output transducer. So the question now, how does that system work? So ask your neighbor, how does that system, okay, we know we have a number of blocks. How does that system work as electronics and telecommunication engineer? Ask your neighbor, because your neighbor is just relaxing. Ask your neighbor. Your neighbor is enjoying life. It's time to disturb your neighbor. Okay. So this is the input transducer. Let me just explain how does it operate quickly, and then we move to the next part. This is the input transducer. The information signal, it depends. It might be electrical, just the input data might be electrical, or might be some other types of or another form of energy rather than electrical form. So once that information is being just fed into the input transducer, will be converted to electrical form, and then that information will be sent to the source encoder. And remember, the source encoder will never understand any other signal rather than the digital signal. So that's why that this one we always call digital data. So this is digital data. And also at this point you have digital data. At this point you still have digital data. At this point you still have digital data. We still have digital data, digital data, and digital data, and digital data. So then the source encoder, the main, just the source encoder actually can perform mainly two functions. And even some other functions, because it depends that you are using the source encoder and channel encoder in which application. But one of the functions of the source encoder is actual to add an address of the information that you want to transmit, whether wired or wireless. But the second function is actually provide encryptions of the information within the digital system itself. It means it provides the security of the information. Then once these informations, which we call encrypted data or encrypted data signal, will be fed to the channel encoder. So the channel encoder will receive the encrypted information from the source encoder with particular address, that particular address where the channel encoder understands it, so that the channel encoder cannot process another signal rather than from its own source encoder. So the channel encoder, its primary function also is this is actual adding an address and also encrypting the information so that may be transmitted safely along the channel. And then after that, remember that this is still information signal. We are going to have a digital modulator where we should have just an oscillator or a local oscillator or RF oscillator in order to make sure that we modulate the information signal and the carrier signal. Okay? Okay? Then after that, the information will be sent to the channel. We discussed about 4 wired or guided medium. We have discussed in previous lectures or workshops. Then the information will be transmitted through the channel, then will be received by the digital demodulator. So the digital demodulator will suppress the carrier signal and allow the information or the digital information signal to be fed to the source or to the channel decoder. So the channel decoder will be, the channel decoder understands, for example, if it is channel decoder X, it's only understand or receive the information from channel encoder X. So encoder and decoder in digital electronics, they work as a pair of shoes. We as the human beings, we have a left hand side, or a lefty, or just a lefty, a left side shoe and a right side shoe. So you have to wear them in pair. In case you wear one pair, in case you wear one type of the shoe, can you? You can't. So it means that the pair of shoes speak the same language. Okay? So this is the first shoe, this is the second shoe. If it is bata, bata. If it is safety boot, safety boot. Can you wear a safety boot and the sandals? One leg you wear safety boot, on other leg you wear just the sandals. Can you? You can't, unless you are doing what? Comedian what? Business. But you'll get surprised if you see somebody who have worn. Sometimes in Bongo we say that you have been a little bit confused. So the function of the channel decoder is actually to decode the information which has been coded by the channel encoder. Okay? Okay? And have the particular addresses for them to speak the same language. I told you that I like encoders because actually they work in pair. And this is the one that gives you the response. For instance, in this space, there's a lot of information signal which have been transmitted. How can you receive yours? How can your mobile phone distinguish your own signal or the signal from maybe the BTS, the nearby BTS, while in this room we have more than 80 mobile phones? So that's what we call it, the power of encoders and the decoders. Okay? And that the power of the address. Power of what? Address. Every mobile calls has its own address or unique address. So the channel decoder decodes what has been encoded by the channel encoder. Right? Right? So we have the digital signal, but remember it's still coded because it has a code of 40 source encoder. And source decoder decodes what has been coded by the source encoder. And then you have output transducer. If the output, for instance, you have a speaker or you have something else which does not understand electric signal, that's why that you need to transform electrical form of energy into other forms of energy that you want to use at the output. Are we together? Yes. That's what you have. We have, I think that the center of this topic is just encoder and decoder. So we'll discuss in detail, and I told you that whether you like or don't like, you'll build a wireless transmitter and a wireless receiver. So you have to encode the information that will be transmitting in the space. So general block diagram of wireless digital communication digital communication system. Digital communication system. So again, this is very interesting because in the wireless digital communication system, the difference is only the mediums or the channel, the modes of linking the information from what? Linking the information from the transmitter to the receiver. So the diagrams or the figure remain the same. The only difference is at this point. For you, you have to redraw the other ones or the new one. And then after having digital demodulator, then we need to feed this information into a transmitting antenna. So will be received by the channel. And this receiver will receive the transmitted information by using receiving antenna. So if that's the case, we'll have figure 3. The general block diagrams of wireless. Make sure that you draw. Wireless digital communication system. Class, is it clear? Is the concept clear? Yes. Okay, so make sure that you redraw it. Okay. So this is the input transducer. Let me just explain how does it operate quickly, and then we move to the next part. This is the input transducer. The information signal, it depends. It might be electrical, just the input data might be electrical, or might be some other types of or another form of energy rather than electrical form. So once that information is being just fed into the input transducer, will be converted to electrical form, and then that information will be sent to the source encoder. And remember, the source encoder will never understand any other signal rather than the digital signal. So that's why that this one we always call digital data. So this is digital data. And also at this point you have digital data. At this point you still have digital data. At this point you still have digital data. We still have digital data, digital data, and digital data, and digital data. So then the source encoder, the main, just the source encoder actually can perform mainly two functions, and even some other functions, because it depends that you are using the source encoder and channel encoder in which application. But one of the functions of the source encoder is actually to add an address of the information that you want to transmit, whether wired or wireless. But the second function is actually provide encryptions of the information within the digital system itself. It means it provides the security of the information. Then once these informations, which we call encrypted data or encrypted data signal, will be fed to the channel encoder. So the channel encoder will receive the encrypted information from the source encoder with particular address, that particular address where the channel encoder understands it, so that the channel encoder cannot process another signal rather than from its own source encoder. So the channel encoder, its primary function also is actual adding an address and also encrypting the information so that may be transmitted safely along the channel. And then after that, remember that this is still information signal. We are going to have a digital modulator where we should have just an oscillator or a local oscillator or RF oscillator in order to make sure that we modulate the information signal and the carrier signal. Okay? Okay? Then after that, the information will be sent to the channel. We discussed about 4 wired or guided medium. We have discussed in previous lectures or workshops. Then the information will be transmitted through the channel, then will be received by the digital demodulator. So the digital demodulator will suppress the carrier signal and allow the information or the digital information signal to be fed to the source or to the channel decoder. So the channel decoder will be, the channel decoder understands, for example, if it is channel decoder X, it's only understand or receive the information from channel encoder X. So encoder and decoder in digital electronics, they work as a pair of shoes. We as the human beings, we have a left hand side, or a lefty, or just a lefty, a left side shoe and a right side shoe. So you have to wear them in pair. In case you wear one pair, in case you wear one type of the shoe, can you? You can't. So it means that the pair of shoes speak the same language. Okay? So this is the first shoe, this is the second shoe. If it is butter, butter. If it is safety boot, safety boot. Can you wear a safety boot and the sandals? One leg you wear safety boot, on other leg you wear just the sandals. Can you? You can't, unless you are doing what? Comedian what? Business. But you'll get surprised if you see somebody who have won. Sometimes in Bongo we say that you have been a little bit confused. So the function of the channel decoder is actually to decode the information which has been coded by the channel encoder. Okay? Okay? And have the particular addresses for them to speak the same language. I told you that I like encoders because actually they work in pair. And this is the one that gives you the response. For instance, in this space, there's a lot of information signal which have been transmitted. How can you receive yours? How can your mobile phone distinguish your own signal or the signal from maybe the BTS, the nearby BTS, while in this room we have more than 80 mobile phones? So that's what we call it, the power of encoders and the decoders. Okay? And that's the power of the address. Power of what? Address. Every mobile calls has its own address or unique address. So the channel decoder decodes what has been encoded by the channel encoder. Right? Right? So we have the digital signal, but remember it's still coded because it has a code of 40 source encoder. And source decoder decodes what has been coded by the source encoder. And then you have output transducer. If the output, for instance, you have a speaker or you have something else which does not understand electric signal, that's why that you need to transform electrical form of energy into other forms of energy that you want to use at the output. Are we together? Yes. That's what you have. We have, I think that the center of this topic is just encoder and decoder. So we'll discuss in detail, and I told you that whether you like or don't like, you'll build a wireless transmitter and a wireless receiver. So you have to encode the information that will be transmitting in the space. So general block diagram of wireless digital communication digital communication system. Digital communication system. So again, this is very interesting because in the wireless digital communication system, the difference is only the mediums or the channel, the modes of linking the information from what? Linking the information from the transmitter to the receiver. So the diagrams or the figure remain the same. The only difference is at this point. For you, you have to redraw the other ones or the new one. And then after having digital demodulator, then we need to feed this information into a transmitting antenna. So will be received by the channel. And this receiver will receive the transmitted information by using receiving antenna. So if that's the case, we'll have figure 3. The general block diagrams of wireless. Make sure that you draw. Wireless digital communication system. Class, is it clear? Is the concept clear? Okay, so make sure that you redraw it. Okay, so then another concept that we need, so this is actual, we say that, modify figure 1. So the next concept that we have learned about Shukuru, about digital electronics communication system. And also we have learned about the nature or the form or the how we get this digital signal. Shukuru, come back please. Then, right now, let us pay attention and pay focus on on the digital electronic circuits for just a moment, because in that digital electronic circuits, we'll find some of the components of these blocks in this block diagram. Have your seat, please, Shukuru. So then, ladies and gentlemen, let us discuss about Samandito, have your seat. Have your seat, please. So define the meaning of digital circuit. Say digital circuit. Say that a digital circuit or a digital electronic circuit is electronics circuit that consisting digital electronics components and a digital signal. So that's the simple meaning of digital electronic circuits. So this is the circuit, or it's a type of this is the electronic circuits that consists a number of digital electronics components and a number of electronics components that process the digital signal. So after learning about the general block diagrams of this digital communication system, after learning about the digital systems, how they exist, how you may define the binary bits with their two states of voltage, then right now let us discuss a little bit about digital electronic circuits in order to understand and in order to comprehend. So simply, this consists of digital electronics. It might be either pure digital electronics components or it might be partial digital electronics components, but the large number of those electronics components must be digital electronics components rather than analog electronics component. When you say digital electronic circuits, it doesn't mean that it does not have analog electronics component. It might have analog electronics component, right? But the main part is actually the digital part, or the digital electronics components, that the point, or that the main part of that circuit. So then, types of digital electronic circuits. Types of digital electronic circuits. So you say that in electronics engineering, there are mainly two types of Samandito, go and clean this dust. And go where you wanted to go. So the first type of digital electronic circuits is called the combinational logic circuit. And the second one is called the sequential logic circuit. Class A, combinational logic circuit. Say sequential logic circuit. Say again, combinational logic circuit. Sequential logic circuit. Okay. So let me introduce you one after the other one. Let us start with combinational logic circuits. Combinational logic circuits. So I know you have introduced these concepts in fundamental of digital electronics, but we need also some skills in order to understand digital electronics communication system. So what is combinational logic circuit? What is combinational logic circuit? Precious, can you tell us? Today it's not Precious. Today it is Namvua. What is combinational logic circuit? Engineer Namvua, engineering students Namvua Omari. So combinational logic circuit is a circuit. It's a combination of the two circuits. Okay. So let me leave this bench. Pasco, tell us what is combinational logic circuit. Can you speak loudly, please?
Combinational logic circuit.
Combinational logic circuits is a circuit which does not have feedback. Yes, which does not have feedback. Edson, tell us what is combinational logic circuit.
The circuit which has more than one logic.
It's a circuit which has more than one logic circuit. Fatuma Makame, what is combinational logic circuit? Fatuma Makame. Engineering student Fatuma Makame. What is combinational logic circuit? Really, if you cannot define, I will go and ask your teacher of fundamental digital electronics. Because I think that you've been learning about K-map, right? So before you learn K-map, you have to learn about combinational logic circuit first. Because K-map is the part. Fatuma Makame. Then Robert, tell us. Engineering students, Robert. At least today we saw you.
Combinational logic circuit.
Yes, combinational logic circuit. Listen.
It has no memory and feedback.
It has no memory and the feedback. According to engineer Robert, the combinational logic circuit does not have memory and the feedback. Shane, who has been in vacation for some quite time, tell us what is combinational logic circuit. No. Tell us what is combinational logic circuit. Combinational logic circuit. No. Just tell us. Don't refer. Yes.
Combinational logic circuit. Hapa ni logic circuit ambayo yenyewe katika output kule kwa hamna feedback inaoleta tena kwenye input.
There is no feedback. Is it an operational amplifier?
Combinational logic circuit.
Is it a closed loop or open loop?
Yani ninachojua mimi ndio ina feedback ina memory.
Nura? No.
It's a logic circuit.
Combination logic circuit is a logic circuit.
No memory and feedback.
No memory and feedback. How much? Pardon, can you speak loudly please? How much? It's a circuit which has no memory and feedback. But what? In addition to that, Dixon? First of all, Dixon Macha Hanarabo. Can you speak loudly? Can you write what you have been saying? Can you write down? Or it will be a long sentence. Continue.
There is no memory element.
There's no memory element.
Example for this
I didn't ask you example. I didn't ask you an example. I just asked you to define combinational logic circuit. Okay. Madam here? Can you speak loudly?
The type of logic
Again loudly.
is the circuit which has no feedback and no memory. Also, the output is not a function of the input.
Okay, so I heard different ways or different definition of how you define combinational logic circuit. So I don't like to say anything about what you've been thinking or you've been saying, but just let me tell you or let me teach you how can you define it properly. Whenever you define about any types of logic gates, you have always to think about about the input, because the definitions is actually constructed from the input. So you have to think about the input and how that input will affect the output. Okay, so it's a combinational logic circuit. We say that a combinational logic circuit, say, is the type of digital circuit in which its output, no any students who mentioned about output, in which its output at any time, no any students who have mentioned about any time, and very important keyword, at any time, depend, no any students who have mentioned about depends only on the combination, depends only on the combination of what? On the combination of its binary inputs, combinations of its binary inputs at that present time. So this is the way that you have defined the word called, or the this type of the logic gate. Class A combinational logic circuit. So this is the one type of the digital circuit in which its output at any time, say any time, say any time. So when you hear the word any time, sometimes it means that In other times, you might find that some of the digital circuits, its outputs change or depends something else. So its output at any time depends only on the combination of its binary inputs. So you may refer what you heard from your friends. There is no any point that we mentioned about memory there. There's no any points that we mentioned about feedback. That's why, but I say it depends on the source of the information that you read. So that's why I said that I have nothing else to say about how you have defined, because I say in most cases, whenever you are learning this stuff, and especially that this high architecture concept, you are always seeking the simplest way to cram or to keep the information in your brain. And I want to tell you that it might be a challenge for you to use what you have been keeping in your mind. Because for these types of the circuits, the only difference, one of the difference, is just how you get the output from the inputs. So these combinational logic circuits always will work depending on the present state. They have any point where they have to work about the previous state. That's a very important sentence or point to take. Okay? Are we together? Yes. Are we together? Yes. Eh? Okay. So the general block diagram, let me just help you or aid you how you can define this terminology by using diagram. Combinational logic circuit. Remember that there are different ways of defining electronics or telecommunication engineering phenomena. It depends about what is your focus. So you should not have a battle that this is the correct, this is not correct. No. Yes, that's why you must read different definition to understand the phenomena. So general block diagrams of combinational logic circuit. So the general block diagrams of combinational logic circuits, mainly it just have 4 blocks. Stop murmuring, stop writing, look on the blackboard. So the goodness of these general block diagrams is just have only 4 blocks. And these 4 blocks are very important for the future workshop or lectures. These are the 4 blocks. Hello? The first block, we call it the input unit, where we have a source of the binary input. The input unit depends. It might be either a sensor, it might be either just a pulse generator, it might be just a logic toggle, it might be some other systems or another electronic system that will be acting as the input of this system. Then we'll have a pair. In many cases, we'll have a pair of the inputs, more than 2 inputs. And this block, we call it combinational. Combinational logic circuit. Combinational logic circuit. And then since this block, we have a block we call the output unit. And in this block, we have the block that called the power supply unit. In most of the online references, they don't draw this block. But remember that any digital system or any combinational logic system cannot work without the source of power. So if that's the case, you say that combinational logic circuits to provide the output, and then you have the power supply, because the input units might be just a pulse generator or something else, might need some power or might not need some power. So this is the simple block diagrams of combinational logic circuit. So this is figure 4, the general block diagram of 40 of combinational logic circuit. So the output of any combination logic circuit depends on the combinations of the binary input. Say it. Inputs. Say it. What did I say? Eliakim, Matthias, tell us. What did I say? Emmanuel Elias, tell us. What did I say? Pardon? Binary input. Okay, so Emmanuel Elias just said binary input. The last two words. Mageni? Mageni is chatting. Zuena? Binary inputs. Wonderful. Lucy, Robert? Binary. What is binary input? Bundala? Bundala? Come back. I say that. Let me repeat. I say that the output of any combinational logic circuit, whether the output of the simple combinational logic circuit or the output of any of the complicated or complicated logic circuit, depends on the combinations of the binary inputs. Bear that in your mind. Are we together? Are we together? Let me repeat. I say the output of any combinational logic circuit. We have simple combinational logic circuits. We have intermediate combinational logic circuit. We have advanced or complicated or complex combinational logic circuit. So regardless whether of its complexity, the output depends to the input, to the combinations of what? Of input. So if you fail to have a clear combinations of the inputs, then don't expect the desired output. Are we together? Then another point that you have to note, we say that we say that the fundamental or the logic gates, all the logic gates that you know, the logic gates are the building blocks of combinational, logic circuit. So logic gates, these are the building blocks. Say building blocks. Say building blocks. Yes, so whenever you think about combinational logic circuit, you think about application or the use of the logic gates. You have learned about NOT gate. Let me just see examples, just remind you, examples of logic gates. Then I will give you examples of combinational logic circuits. So you have learned about NOT gate. NOT what? NOT gate. Then the next question after you have understood NOT gate, where can you use NOT gate? Okay? So one of the use of the NOT gates, you can use NOT gates in designing combinational logic circuit for the particular purpose. You have been learning about AND gate. Say AND gate. So what application, why did you learn about AND gate? Did you ask yourself? Did you ask yourself? Somehow. Others, you didn't ask yourself. You're just waiting. How many questions of AND gate will I find in the exam? That will be your discussion. Then you'll be learning about what? OR gate. So what the function of OR gate? We use OR gate in designing combinational logic circuits. So NOT gate, the outputs of NOT gate depends just the combinations of its inputs. The output of AND gates depends on the combinations of what? Of the binary inputs. So Matthias is conducting another class to Zuena. Number 4. Then we have that you have learned about NAND gate. Say NAND gate. Say NAND gate. And maybe you have verified it's true stable. Then after verifying it's true stable, where can you use it? Why do we have NAND gates in the world of digital electronics? Then you have been learning about NOR gate. Say NOR gate. Say NOR gate. You've been learning about exclusive OR gate. You've been learning about exclusive NOR gate. So the primary applications or use of these logic gates is actual to design what? To design combinational logic what? To design combinational logic what? Circuit. So Gertrude, tell us, what is combinational logic circuit? So Gertrude will spend some time to log the information. What is it? What is it? So she's referring the exercise book. That's indicate that Gertrude is tired. Okay, then let me give you some examples of combinational logic circuit. I know that you have learned them, but you didn't learn them with the comprehension that these are the combinational logic circuit. You just learn the system itself. So we have a number of examples. The first one, the simplest example is called the half adder. Say half adder. Say half adder. You have learned about half adder, but you don't know that's one of the example of combinational logic circuit. Or maybe you know it. Then the second example, we call it full adder. You like this stuff, eh? Full adder and half adder are simplest combinational logic circuit. But after full adder and half adder, there's another story now. Yes, needs your seriousness. Then the next example, we call it BCD adder. Do you know BCD adder? No. You don't know. You have to know it. What the long terms of BCD? Binary coded decimal. So after learning binary coded decimal, where can we apply it? In hospital, eh? Okay. We apply this in hospital. To do what? They are just integrated within that biomedical equipment. Then another example of class A half adder. Say full adder. BCD adder. So if you have learned about BCD, but you didn't learn about BCD adder, then you are still lacking something. The other one is half subtractor. Kankesha, come on please. Say half subtractor. Okay, go. Go, Kankesha, go. Kankesha, come on please. Kankesha, go. Then the next one is full subtractor. Matthias is good. Okay, say full subtractor. Half subtractor. Then the sixth example of combinational logic circuit. This is the one of my favorites. My favorite combinational circuit is called the encoder. Say encoder. Again, say encoder. So once you hear about encoder, the next pair is decoder. So I told you that in case you get the identical twins, don't bother about 30, finding the names. That Jacqueline and Joan. No. Just call encoder and decoder. Very interesting name. And actually, I think they will have a special anointing on electronics engineering. Is it? That is okay. Say encoder and decoder. Number 8, we have another one which is called the multiplexer. Say multiplexer. Say multiplexer. Have you ever, so ask your neighbor, have you ever seen multiplexer? Where did you see multiplexer? Home. Eh? Do you have multiplex at your home? Can you bring it for me next Monday? Why? Eh? You cannot carry it. Then the 10th example, these we call them digital comparators. And the 11th example, we call them magnitude comparators. Precious, come. Magnitude comparators. Say magnitude comparators. Have you ever heard about magnitude comparators? No. So what do you used to hear? Different inputs, eh? So most of these combinational logic circuits are used in designing digital electronics communication systems. Okay? Yeah, so that's why we have mentioned. But specifically, we'll be discussing in detail or deeper about encoder and decoder. That is great. Yes. Yes, you may ask a question. Okay, who can answer Oro's question? Oro ask a question. Why the inputs has 2 arrows? Why are the block between the input unity and combinational logic circuits or combinational logic unity, there is the 2 arrows? What do they signify? And sometimes not 2 arrows. Sometimes we write that this is an input. And what does it mean? Sequential logic circuit. Alphonse, tell us. Hatimaye, Alphonse has been seen. Alphonse, tell us. Okay, thank you, Mr. Alphonse. Then Samuel, tell us. Ringo. You have been lost. You are around, eh? Live. Ringo, tell us. No idea. Fatuma, Mwenye Mkuu. Nation, tell us. Why do you have 2 arrows there? Glory Pimaro, Glory Pita Maro. Tell us. Pardon? You are not sure. Okay, tell us what you are not sure. Okay. So the response is this one. For instance, listen, why do you use either n inputs or 2 arrows to indicate the inputs in the combinational logic circuits, so in most of the digital circuits? This is the reason. For instance, we use, these are the fundamental functional blocks or building blocks of combinational logic circuit. I've mentioned 7 of them. It's only one that's called NOT gate, which has only single input and single output. All the other logic gates, which are actual 60 logic gates, the minimum number of inputs is 2. They might have 2 inputs, they might have 3 inputs, they might have 4 inputs, they might have 6 inputs, they might have 8 inputs sometimes. So it represents the arrows, or the arrows from inputs to the combinational logic circuits is actual to represent the reality. To represent the what? The reality. So which kind of the reality? We're expecting to have more than one binary input in order to combine to get what the output. Then, so is it clear? Okay, so all have understood. Then class A sequential logic circuit. Say sequential logic circuit. Dixon, yourself, Dixon, Diego. Say sequential logic circuit. Again. So define sequential logic circuit. So listen, a sequential logic circuit is the type of logic circuit in which its output depends on the combination, because if you ask a question, you'll just tell me that that one has feedback on the combination of binary inputs, on the combinations of binary inputs and the previous state of 40 of the inputs, previous state of the inputs that has been stored in the memory. Where do we find combinational logic circuit? Take your scientific calculator. How many of you have scientific calculator? Take your scientific calculator. Take your scientific calculator, the one you use to answer the questions. It's far from you. Anyway, the main circuits mean that the motherboards of the scientific calculator consist in a number of combinational logic circuits. Why? Because the primary function of scientific calculator is actually to perform the calculations or the computation. In case of the computer, we have a general blocks of diagrams of the computer. One of the blocks of the computer is called the arithmetic logic unit. So arithmetic logic unit, it means that the logic circuits that used to build up the arithmetic logic unit is what we call it combinational logic circuit. So in scientific calculators, actually the dominance, or it means that the king is combinational logic circuits rather than sequential logic circuits. That's why your scientific calculator cannot store memory for the long time. And in case of the computers or mobile phones, we have a block, we call it arithmetic logic unit. So you say arithmetic, we means about arithmetic operation, which means addition, multiplication, division, subtraction. Okay? When you say logic, we say that we say that logic operation, we have AND logic operation, we have OR logic operation, we have NOT logic operations, we have exclusive OR logic operation. So we have gates and we have operation. Hello? So if you've been engaging yourself with computer programming, you may understand when I say that we have operation, logical operation. But if you did not engage yourself in in computer programming, and especially to combine more than one statements logically, then when you say that we have logical operation, you may not understand. Because sometimes you may take one sentence and then you end with another sentence. Or you may take one condition, then you end with another condition. Or you may take one condition, so you OR with another condition. In computer programming, that's what we call it embedded. So in embedded computer programming, we are using them often. And the way actually it operates is according to the truth table of AND gate. So my dear students, you have to understand we have logic gates, we have logic operation. Say logic gates and logic operation. When you talk about arithmetic, actual that you know, you're expert because we met during primary school. Addition, subtraction, multiplication, division, right? Greater than, less than, right? Those we call this inequality. Greater than or less than or equal, not equal, equal. So when you talk about logic operations, that's what we mean. We have mainly AND or not. And in some situation, you cannot write a computer program and not using this logic operation. And actually, they work according to the truth table of the AND gate, truth table of OR gate, truth table of NOT gate. Are we together? Are we together? Remember that in logic, we don't have, or in logic operation, we don't have subtraction, also we don't have division. We just have addition and the multiplication. Your scientific calculator is actually performing addition and the multiplication. However, yourself who is inserting decimal number, you may see the multiplication, you may see the subtraction sign, you may see the division sign. But actually in logic phenomena, we don't have subtraction, we don't have division. Why? Because subtraction is just repetitions of addition, of just addition of the numbers. Why? Division is just repetitions of multiplication of the numbers. So subtractions is performed by using addition, and the division is performed by using what? Multiplication. I don't have permissions to go further and further because I'm not teaching about digital electronics. I'm just teaching about digital electronics communication, right? So I just gave you a catalyst. Go further. So we say that a sequential logic circuit. Say sequential logic circuit. So this the logic is the types of logic circuits in which its output depends on the combination of binary inputs. So its output firstly depends the combinations of binary inputs. That's number one. But number two, its outputs also depend the previous state. Say previous state. Previous. Say previous state. Previous. Say previous state. Previous. Previous state of what? Of the binary input. That has been stored in the what? Memory. Are we together? So whenever you want to understand about sequential logic circuit, you have to understand how you can combine the present binary inputs and how also you can combine that present binary inputs with the previous state which have been stored by the memory element. So if that is clear, then the general block diagrams of what? Sequential logic circuit. I'm about to end this class. Sequential logic circuit. So in the sequential logic circuit, stop writing, look here. We are just adding another important block. And this block we call it memory. So then, once we combine, for the first case, once we combine more than one input as a present state, we'll get the output. That output for the first case will be stored in the memory element. When we ask it it means we ask it the sequential, or just we feed the second input, or we feed the input for the second time. Then this combination of the inputs with the combinations of what has been stored in the memory will be fed together into a combination logic circuit and will provide the output, which is the outputs of the sequential logic circuit. So sequential logic circuits is actual combination logic circuit plus the memory element. So we have to fit what the previous state of these logic circuits, which has been studied by what? by the memory element. So you have to be careful because in the next academic year, in your second year, you'll have a module called the digital electronics. It's no longer fundamental, it's called digital electronics. And the heart of that module will be on sequential circuits. And that's the moment you'll be designing about counters, designing about designing about flip-flops. So you'll be dealing with the different logical circuits. So when the system being initialized, no any difference from the memory state, right? It will give the outputs. Then that outputs will be stored in the memory elements. When the second operations will take place, we have the previous state from the memory elements, we have the binary inputs, right? Being combined together logically according to the combination logic circuit that you have, then we have a new output. When we feed the inputs for the said time, then remember that the second outputs will be stored. Hello? Will be stored in the what? In the memory element. So the second input will be fed as the previous state and being combined with the third binary inputs to give out what? The outputs. That will be the third output. Then the third outputs, the state of the third outputs, whether it is high or low, will be fed to the memory elements. Jessica? And then for the fourth times, we have our first combination of binary inputs, then combines the third previous state, right? And let's give the outputs. So that's how the system will be working continuously, day after day, hour after hour, years after years, and even decades after decades. Is it interesting? And to hear it's simple, but to make it, it's another story. So this is figure what, ladies and gentlemen? Figure 5. The general block diagrams of what? So in case that you forget, just today, you may call your neighbor. I will call you sequential, you will call me combinational. So sequential, logic circuit. So just I will call you sequential, tell your neighbor. I will call you sequential, you will call me combinational. I won't call you precious. So let us end this class with examples of sequential logic circuits. The first example is called, the simplest one, is called the flip-flop. Say flip-flop. Flip-flop. Say flip-flop. We'll be reading the history of the memory elements or the computer memory. The first one was called the hard disk, not the hard disk actually that we use the tapes. Later on that computer used this something called a flip or floppy disk, right? So floppy disk is nothing, it's just the flip-flops within. So for those newborn babies, flop disk is another vocabulary. Then another ones we call them registers. Say registers. Say registers. They have nothing to do with registration. So don't say that registers is just registration. Then we have also something called them counters. Say counters. That's another example of sequential logic circuits. So we have counters, we have registers, we have flip-flop, counters, yes. So in case of the flip-flop, for instance, we have 4 flip-flops in electronics. We have SCR flip-flop, also we have T flip-flop, and also we have JK flip-flop, and also we have another ones which is called the D flip-flop. D flip-flop. Say flip-flop. Say flip-flop. So we have counters, Others, how do we call them? Counters, registers, flip-flop. Say registers. Say registers. Say counters. In counters, we have up counters, we have down counters, we have up, down counters. Can I repeat? Dennis is not writing and then say no. We have up counters, say up counters. We have down counters. And then we have up, down counters. So you used to have stopwatch. Say stopwatch. Do you remember stopwatch in physics experiment? So they can count up or they can count down. So within those stopwatch there is count up or up counter and down counter. And they are digital system. Class, is this concept clear? You have a foundation, a good foundation of digital electronics communication laboratory or digital electronics communication system. Do you have a foundation? You have some ABCD, okay. So in the next workshop or lecture, that will be lecture 2, we'll actually pay attention on key focus on one of the digital electronics communication system, and hopefully I will be rushing towards the encoder and decoder because that is the one you don't cover in maybe some other modules. So let me know. Did you understand the concept? Yes. Wonderful. So if you have understood, thank you very much. I would like to take this opportunity firstly to thank God. Frankly speaking, and just let me say that the truth. When I started this class, I didn't think that even I can teach you for 10 minutes because I was feeling a critical headache. But I thank God that now I'm healthy and kind of I'm fine. So I thank God who have given me this opportunity to teach you, and I would like to invite you in the next class so that make sure that you join with us, make sure that you go further and further and you dig the concept. I don't have any homework. The homework that I want to leave to you, just to go and do the further studies of what we have covered. In case you have any challenge, let me know. So I would like to say that this is the end of workshop 1 or lecture 1 of the digital electronics communication system. So it's better because we are heading to the weekend. First of all, tell your neighbor, I need you a happy weekend. I wish you a happy weekend. Tell your neighbor again, I wish you a happy weekend. Tell your neighbor, I wish you a happy weekend. Okay, thank you very much. Let me see you next week.
Hekima, umoja